back, and as you can maybe see, I've started a recording on this one. So in the last session, Microsoft showed that they were more interested in developing our AI than continuing to support Teams. So I found myself in a situation where about half the folk could jump on and attend. No idea why. If you are part of that cohort, you're back today. Thank you very much for coming back. But I will publish this after that experience last week. So I think that we're good. I'm just going to do a final mic check. Anyone? Diane, thumbs up, hand up, anything you like. Anyone else? Just to make sure. Cool. Thank you. We're good. We're good. Okay, so some of you know me. Some of you don't. My name is Darren, and I'm one of the team behind this platform that used to be called Speckle. It's now called Better Building, primarily just because we've gone to the US now, and we needed the platform to be a bit more visible. We had this awkward situation as well, where there was this crowd in London that was also called Speckle, spelt slightly differently, but they got like a £30 million round of funding or something like that, so there was no way we were going to compete with them. So anyway, there you go, a bit of background. I've thrown the old microphones on today, the videos are on, so I'm more than happy for this to be a fluid session. I don't mind people voicing their opinions about anything. And I was just going to go through a few introductory slides here just to kind of explain what the session is about. So just some rough numbers here, first 45 minutes. I wanted to go through and kind of explain and maybe have a discussion around some of the changes that we're seeing come through on this H1 verification method and some of the things that you need to look out for. So this is all applicable, whether you're on the platform or not, doesn't make a difference. This is all useful information for everyone to understand. And then the second part of this session, again, rough numbers for the 45 minutes, depending on what we get into. We'll go through some practical examples. So I've got a couple of practical examples here set up, but I'm more than happy to hear from folk that want to look at specific things. So I'm going to ask that question at the end of the first 45 minutes. Now, of course, if you haven't been on the platform, we have a website. You can go ahead and look at that. And we have a bunch of folk on there. I'm not going to overly sell anything here now. I'll just make a couple of points on the fact that we have a bunch of points of interest, really. Energy, which is the context of today, so H1, maybe AS1 and VM1 for New Zealand. And then daylight, also we do the G7 stuff, but we also do moisture calcs, we do carbon calcs, we do advanced HVAC, and we've got this kind of project management workflow as well, called flows, that allow you to go ahead and kind of use your energy models, daylight models, and track them and assign tasks to them and store documents, and that's a growing part of what we do. There you go. There is a website, betterbuilding.io, Indian Ocean, if anyone was wondering what the IO was about. And you can go ahead and sign up. If you do sign up to the New Zealand platform, and I'll send you over a link to this in a second. There's our documentation. So that's my effort on a sales pitch. It wasn't amazing, but I'm not very good at sales, to be quite honest. I'm going to turn off the camera now, just so I can kind of focus on this. Now, let's get into H1 VM1. Guys, has many folk, and this is an opportunity to raise the old hands, has many folk jumped in and had a look at this yet? If you have, this might be a good point to kind of give us your opinion. So anyone across this yet? No?
Yep, I've had a look.
Cool. What do you think?
I think at least they put in the increase of timber framing,
Yep.
at least,
Yep.
you know, but I still don't think it goes far enough, because I still don't think they've actually addressed that VM1 doesn't reflect the real world of modelling yet.
Yeah, modelling is always difficult to reflect the real world, because the real world is a very, very dynamic thing. But yeah, I agree. It's definitely a step in the right direction. Anyone else though had any experience in this yet? If not, I'll mosey on through and. Oh, Salmon, Salomon. Sorry. Did you have a look as well? Or were you just unmuting? No. Okay, cool. So let's get into it. So, as some of us know, it being VM1 is just a verification method, and it's a compliance pathway for H1. It is, for all intents and purposes, exactly the same as an acceptable solution. Now, VM1 has drawn some attention over the course of the last couple of years as it's become a wee bit more popular, just because from a council perspective, there's a lot of unknowns in there. So councils have been grappling with the fact that there's a few unknowns in VM1. They're not real unknowns, they're just a lack of confidence in terms of reading reports, and probably how variable reports are from a VM1 perspective. So Auckland Council specifically have voiced the need to have PS1s provided for VM1. Not justified from my perspective, and that's only because, purely from a compliance pathway perspective, the acceptable solutions and the verification methods are exactly the same. I do sympathise with the fact that there is more information in VM1 and they're harder to read because the more inputs need to be qualified and there's a lot more outputs as well. But for all intents and purposes, they are one and the same. Now, as you'll note, they are for buildings up to 300 metres squared, so housing primarily, or I guess buildings connected to housing, the occupation of a space that is equivalent to a house, because you can do communal housing, that type of stuff through this as well. So there have been some quite significant changes between that on the left being the 2022 version and that on the right between being the 2025 version. The one thing they have in common is this horrible green that seems to be chosen each time they publish these. I don't know why they choose such a horrible green. But the positive side of things from a H1 perspective in general is that the schedule method has now been removed. I say that's positive just because H1, the schedule method in H1 was only providing a very opaque compliance pathway, whereby which it was hiding certain elements of design, which actually continues in part the narrative for the calculation method, and it was certainly leading to good outcomes if you design properly, but terrible outcomes if you didn't, and often over-engineering buildings as well. So it was one of these pathways that obviously has been around for a long, long time, that effectively just didn't work anymore, because you cannot start to push towards higher performance buildings without designing them. You can't just throw thermal insulation and high performance windows at a building without designing that building, or you result in overheating and poor design outcomes. So it's great to see that gone. I'm not going to talk about it anymore. The calculation method, that has I'm not going to talk about that. It's not gone from the methodology at the moment. It's still there. I actually, just to go back to that, I actually believe that the calculation method is going to be the only method really adopted in New Zealand, and that's saying something, because we focus on the VM1, but I think from a reality point of view, with the adoption of AI, people are just going to be throwing models at the calculation method just because it's so easy to do. That's not to say that there won't be unintended outcomes as a result of doing that, but I think that's where the market's going to go. We of course think the modelling method is the best way to do this. So if you're experienced in this space, you might be using our software, you may be using PHPP, or PHPP in the Echo software, and they are all doing the modeling method. I've got no insight into what folks are doing in terms of the reference and the proposed design in other workflows. I can only say from our workflow, we've gone through a process of working with MB to fully understand how to deliver effectively the reference building to compare to. So for folks that are not familiar with the process, you got a reference building, you got a proposed building. I'm calling them designs on this slide here. And effectively you're comparing them to get an accumulative space heating load and cooling load. So two designs, you compare those space heating loads and cooling loads in order to effectively calculate the sum of them and state whether you comply. So in other words, your proposed design must be better than the sum of the space heating loads and cooling loads than the reference building. So there's lots of stuff going on here. Now, when it comes to VM1, practically speaking, there's a bunch of things that you can look at and can vary from the proposed design to this reference design. So in other words, the next sequence of slides that you're going to see are very much around the things that you can potentially improve. So you can potentially improve the wall construction, R value, and thermal mass. Quick note on the thermal mass is that the thermal mass is defined as being a lightweight wall. We've offered values to determine whether the values that we understand to be a lightweight wall to MB, and we're kind of waiting for a bit more confirmation on that. We have had confirmation that the values that we have provided are acceptable, but we haven't implemented them yet. So for any folk out there that are interested in thermal mass, we would like some contribution to this conversation, because we won't lock in any lightweight thermal mass until we get more market buy-in. So the other thing that can change is floor construction R value, really important. I'll come back to that in a second. Roof construction R value and thermal mass, not sure about the thermal mass side in reality, but the roof construction R value can vary between the proposed and reference and provide you a point of value. The next one, big one, glazing, big tick in the box there. That's the one of the big ones that need to be focused on in terms of the proposed design, but you can also obviously improve doors. I don't know, it's very difficult to improve doors. When I talk about doors in this respect, I'm talking about opaque doors, your classic entrance door to a property. They're very, very hard and expensive to change, but defaults of an R value of 0.3 are typical, which is pretty bad, given that an R value of a wall is 1.6. Skylights can be improved. Construction R values for those windows. Solar heat gain coefficient's a big one as well, and external shading. So all of these things can be improved against the reference building. And then we have heating, cooling, and ventilation. That's a statement in VM1. Effectively, you can ignore that because that's automated in the VM1 methodology. So the point to take away from here is the reality. And I say the reality based on the fact that the wall construction R values, the roof construction R values are already in ballpark better value land, and they're difficult to improve for standard construction methodologies. The floor construction and the glazing systems, maybe skylight systems as well, can be improved, and they are, from my perspective, the points of opportunity to improve the proposed design against the reference design to meet the compliance pathways of the code. Okay, so they are the big ones. We can circle back to those at some point. Now, my reading of the code itself is that, hey, there's probably about 10 things that are opportunities to, or there are 10 things that we need to understand that have changed. Now, as of a couple of weeks ago, we've already launched all of this on the platform, so you really don't need to worry about any of this stuff on the platform. It's all already automated for the reference building, and you can check it out yourself. But the first thing is that the climate data has changed, and It's changed in terms of it's just being more specific about which climate data we should be using, right? And they've just referenced the NIWA climate data there, which is fine. And if you are over in other software, you have to convert from the NIWA climate data over into the weather file format of that software in order to effectively be apples for apples on this particular point. So not a big one. Fortunately, the climate data is provided. It's provided in a list in VM1, so that's a good thing. It is clustered a bit, so you can see here, for example, the far north, Auckland, all the way down to actually these top three here are all the same climate data. Auckland and what's that, Thames, Coromandel district, that's all the same climate data, and all of these ones down here are all the same climate data. So it is fairly simplified, and I'm not in a position to say how accurate that is. But the other point here is that you can grab access to these climate files, so they're freely available. Go ahead and locate those. They're on the Building Performance website, and they're very, very easy to find. So have a look at those. And that's climate data done, out the way, 9 more to go. Next up, solar heat gain coefficient. This has been a bit of a bugbear of mine, to be quite honest. There's a hand up there. Diane, did you want to get into that one?
It was just about solar heat gain. I've actually put a thing in the chat, but you're already going to talk about it, so that's fine.
I'm probably going to complain about it, but
Yeah, exactly.
So all good. So solar heat gain coefficient has been a really interesting one from my point of view, because the New Zealand industry in general has not been overly aware of solar control in glazing. It has definitely become much more aware of thermal performance or total R value, construction R values for glazing systems, for joinery systems, but it has not been fully aware of solar heat gain coefficients. And I've been in position multiple times where I speak to architects and they don't have an exposure to solar heat gain coefficient. And I think that's going to change now, because effectively the numbers have been determined for the reference building, which they hadn't really before, right? So there was flexibility, and the new number for the reference building is 0.55. Okay, so that needs to be locked in now. And if we have a quick look at solar heat gain coefficients, and I'm just going to highlight here really what are typical solar heat gain coefficients from a home perspective. Okay, so you do have numbers outside of this range, but effectively between 0.4 and 0.7 could be deemed as being typical. Now you'll note there that I pop on high for 0.55 to 0.7 as a rating, and moderate as 0.4 to 0.55. The reason I do that is that the moderate, from my perspective, is where all homes should be. No home should be higher than 0.55 under any real justification, unless all glazing is facing towards the south and there's no risk of overheating. Diane, did you want to jump in there?
I'm not disagreeing with anything you're saying, and I agree in terms of the moderate and the high, but my argument is that solar heat gain coefficient should not be in our code. It should be G value, because that's what we use in New Zealand glazing, not solar heat gain coefficient. And they can end up with different numbers. And if you compare like with like, because solar heat gain coefficient is based on a US standard that we don't use in New Zealand. Hence, G value will give better results. So I guess I'm frustrated that solar heat gain coefficient is still in the code.
Live that frustration. So I would agree, if there is any standardization, it should be undertaken. G value, solar heat gain coefficient, solar factor, and Diane, you'll be you'll be enjoying the fact that I'm picking up on what you're saying here in this next slide. The fact that even one of the most common suppliers use the term solar factor. It's not a G value or a solar heat gain coefficient. They've determined it as a solar factor. So this is doubling down or tripling down on my point around the fact that the industry has not locked down some standard vernacular for what they want to determine technically from a heat transfer perspective for glazing. And yeah, I agree. If G value is what is used, absolutely use G value. Don't use solar heat gain coefficient. And there was only a small change between it. It's a technical change between what a G value will represent versus what solar heat gain coefficient will represent. But Diane's point is that it should be standardised. Okay, so if we go into just some standard systems, clear double glazing, 77%, way too high. This Thermalite, low E, triple glazing, 49%, that's in the ballpark. If you're down at 36%, you're getting quite low, so you might be losing out on opportunities in terms of heating the building through solar gain. And if you get down at 21%, you've got really quite dark glazing, and you're very, very unlikely to want 21% given that the reference building is 55%. So you probably would never pass the reference building. So yeah, there you go. That was solar heat gain coefficient number 2. Number 3 is the modelling method requirements. And so this is really just looking at, I forget what, I got it. So this is really just looking at ventilation. And I'm just going to flick through to the next part of this here. So ventilation from a window perspective has been treated as having a number of 24 degrees as when a window is perceived to be open. And ignore the word salad on the screen. So 24 degrees, and then it was perceived to be closed by modelling methodology at 25 degrees. So that is effectively a maximum of 1 degree when the window can open. Okay, that's now changed, and that's an important change because it will fundamentally change the outcomes of the model. When you only have a window open between 24 degrees and 25 degrees as per the previous version of the code, then it means that you're going to build up heat within that space, and you're only going to purge the building between 24 and 25 degrees. But now the 24 has been adjusted to 22. So what that means is that theoretically both reference and proposed design will be opening their windows at 22 degrees and closing the windows at 25. That doesn't seem like much, but what it means is there's going to be a big theoretical purging of the buildup of heat within the space that effectively artificially cools down the building and reduces the cooling demand. Okay, so it's a very, very important one theoretically because it means that there's a significant change in the design. Now, there hasn't been, and you can continue to ignore the word salad on the screen, there hasn't been a massive amount of support in terms of the types of windows, the percentage of opening of windows in H1 in general. So that is a market-based discussion about when things are open. Our advice is to always veer on the side of caution and just assume that effectively windows are only going to be open a small bit, and the last point here is that window restrictors are probably a good way to assume that. So don't overestimate how long your windows and how open they're going to be. Just be conservative about this particular element. Now, I think there's another quick slide here in terms of the difference between that 24 and 25 and 22 and 25. And this, I think this was in New Zealand, and it just shows there that there is a decent difference in cooling demand when it comes to the difference between these two scenarios. So it will change the outcome, and it will mean that the design opportunity that is potentially there today is no longer going to be there with the new version of the code, because the code is not overemphasizing cooling anymore. Okay, so via VM1 there's going to be a reduction in cooling, which is fine because it was overstating cooling requirements anyway through the 24 to 25 degree scenario. Bit complex. Is that one okay, guys? Is anyone throw up there? I think we've got a hand up there. Is that Maria? Is that you?
what I feel is a stupid question.
No, not at all.
Does this modeling always rely on you having a continuous ventilation system? Because given that in the general building code, we don't require continuous ventilation, so the code allows people to open the windows and requires them to open the windows every day just to ventilate the house. And I'm just listening to this and I'm just like, so this is only for when you have continuous ventilation running, or is this applied to?
No, this is only Windows, Maria. This is only Windows. Sorry, just nothing to do with continuous ventilation and HRVs, that type of thing. Nothing to do with it. It's only continuous ventilation. Sorry, it's only window ventilation. Nothing to do with continuous.
But we have to open them anyway, regardless of what temperature it is outside.
It's just assuming that this is indoor temperatures, and it's assuming that people are going to be there, and they're going to open their windows in order to purge the heat between 24 and 25, and that's now 22 to 25. It's not really assuming anything else. It's just, this should not be in the code. This should not be in the code. To assume ventilation at all is just assuming that occupants are going to do something about their comfort, and you cannot state what people are going to do. So I think it just acts as a point of confusion, and it's a bit of a red herring here. And yeah, should not be in the code. So continuous ventilation, there's nothing there in the code for that, unfortunately. This model can be used for that. All you would do is effectively get rid of this in the model and apply an HRV to the model in order to get the benefit of it, and it would be significant. It would be absolutely significant. The only place this is really of value, I think, is within maybe bedrooms or something like that, where you assume at night people are going to open their windows by a crack, and that's it. So a very local application of it, pretty much as you would do if you were designing in Passive House, for example. Hopefully that answers your question. I'm going to move on to occupancy and plug loads. Now, there is actually a bit of a Passive House overlay to this particular one, because what we had in the previous version was really, really high internal gains from occupants and from plug loads. Now, there's been a couple of changes here. The big one is plug loads, and the much, much smaller one is just a determination of the occupancy. So when we look at plug loads now, you see that value 13.5 over there. That used to be 24.5. So what it means is, theoretically, we're not dumping loads of heat into a model that we then get benefit from, and then we have to purge as well. So they've pretty much brought that down significantly. So 24.5 down to 13.5. And on the occupancy side, they've just made it a little bit simpler and brought the values down as well. Well, I'm not sure whether that's absolutely true. They've clarified the value here where they hadn't clarified it before. They've done it in a slightly different way. So I'm not sure the difference actually between the two versions for the 2.5. But anyway, that 2.5 was not there in the previous version. It was described from a methodology in another way, but now it's just a little bit clearer. But the 13.5 is significant, and when it comes to the occupancy, the only thing that's been addressed here is that for some unknown reason to me, 12 a.m. to 8 a.m. for housing occupancy from Monday to Friday, Saturday and Sunday was previously 1, and it is now 0.7. So I'm sure there's a story, there's a narrative behind that. I do not know what it is. All I can say is that 0.7 was 1 at one point. So for some reason, 30% of the people are leaving the house at night. Don't know. We can make up a scenario as to why that's happening. But that is that. So that's handled anyway in the new version of the code. Next up, another easy one, which is the thermal envelope itself. Okay, so a couple of tweaks to the construction R values. And I think Diane was bringing up this straight out the gate, just in terms of the wall R values. So we have 1.6s instead of the 2s. I think the 2s and 2.2s. I forget now what the previous versions were, but it's pretty much 1.6s across the board. And I'll go into the narrative as to why that is in a couple of slides time, but effectively the reference building is now saying 1.6, so it means that it's just a little bit more relaxed. It shouldn't be. They're pretty low values, to be quite honest. I don't think values below 2 should be justified, but they are what they are. It feels like a bit of a political hot potato, that one. Heated floors, here we have a clarification, guys. The clarification is just essentially that previously, if you were going to heat floors, it was unclear how far you needed to expand your insulation strategy for the heated floor. So, for example, if you had a heated floor in your bathroom, did you have to effectively insulate all of the slab, or was it just part of the slab? And obviously that doesn't make much sense, insulating part of the slab if it's just a bathroom. Here they're just saying that, hey, look, minimum construction R values do not apply to heated ceilings. Question mark, I still don't know what they are. Heated walls, still don't know what they are. And heated floors, as if they are kind of solely, if the heated floor is installed solely in rooms that only contain a shower, bath or toilet. So just a bit more of a relaxing there. Next up, we have multiple unit dwellings, and this is just again a methodology thing. So if you have a dwelling, if you have a model and it's for housing with multi-unit dwellings in this particular case, the new version of VM1 states that the building may either be treated as having a single thermal envelope, and that's very, very much for the passive house community, or having multiple thermal envelopes with different housing units having their own thermal envelopes. So it's saying that there's two methods there. I absolutely disagree with this. I think it's absolutely crazy to model a multi-unit dwelling as having a single thermal envelope, because effectively these are owned by different people. So if you have a single thermal envelope and you split that up into different internal envelopes, then you're going to get a very different thermal response within each of those spaces, each of those homes, each of those apartments, and they must be designed individually. This is not what this states. This states that you can just dump it all into a single thermal model. So it makes it much easier from a compliance point of view, but does not cover the basics of occupant comfort when people are controlling these different units, different apartments individually. So for me, this really doesn't make any sense. Excuse me, I've just gone backwards. And then all we're stating there is that instead of having separating these out, and this is just an example, you can go ahead and just run your thermal model as a single zone. Makes no sense to me. Anyway, before I continue, I was just going to shout out, if you want us to jump in and do some free modelling for you, there is an opportunity at the moment, just because we're testing out a lot of converters. Converters from a market perspective means that we're looking at ways of improving the drawing process. So if you want we want to get access to DXF files and PDF and PNG and even Rhino files. In order to import, we'll manage it ourselves and give you the model back, and the benefit is that you get a model done for free, and we get the opportunity to test our various converters that we're working on the back end. So it's a broad 6-month project that's going to allow us to effectively build out automated processes without being slaves to AI, and do things in a much more engineered way in order for us to then provide a service back where effectively you can automate your own processes without having to redraw models, because no one wants to redraw anything. Why would you? So that's what you have to do at the moment, but we're going to be offering that service to hopefully apply much more fluidity in the compliance process. Now, we're going back to the walls now, and we're looking at I guess really there's two items here. There is a direct modification of the 4214 standard. And there is probably something, I guess, that Diane was alluding to, is that R1.6 for the walls, so mentioned a few slides back, default now for the reference building, where it effectively comes from, in my view, is that if you throw in a bat into your 90mm stud wall, that bat has a R value of around 2.2 with a 38%, which is an industry adopted value based on research done by, I forget who it was done by, feel free to shout out anybody, but they...
Placemakers using their frameology.
Thank you, yeah, exactly. So they determined the average thermal bridging through timber stud was around 38%. So effectively, if you throw in an R2.2 bat into a 90mm stud, you'll get a value of around R1.6. That's my technical read of it, and what it does, it allows, I guess, the market to start looking at how to reduce that thermal bridging from 38% back down to much lower values. You should be able to get back down to 18% pretty quickly, and I guess the view there is that it would provide an ability to meet compliance via the verification pathway in an easier way. What I would say though is that typically walls are not the most sensitive element. So if you are playing around with trying to improve your thermal bridging, while you should do that, it's a good thing to do. It's only going to be maybe 10% of your potential heat losses, subject to the type of building, of course. But because the slab, the roof, and the windows are such a high proportion of your overall heat transfer, you're effectively playing around with very, very small numbers to get very small improvements. That is not to say you shouldn't do it. It's just to say that from a compliance point of view, it's probably not going to make too much of a difference. And the other point in the NZS 4214 is that, a little bit annoyingly, they've just introduced some new wording methodology that that supersedes, I should say, the clauses directly within 4214. So I haven't gone into them in detail here, but it's just this modification that they've made, and you'll need to be aware of that when you're undertaking 4214 calcs. And arguably, I don't know why NZS 4214 is still included in the code. There was talks, and we as a company attended those talks in terms of superseding it with the calculation methodology within PHPP, which I completely agree with, but that hasn't been adopted here. 4214 is a very old standard and has lots of questions around its useful application, particularly in commercial buildings. Now, getting to the end of this is 9 out of 10, guys, and then we'll stop for a few questions and then provide an opportunity to have a quick break, glass of water, and then we can jump into the second part of the session. So internal dimensions, this is just clarification. Internal dimensions should be used if you want to, I guess, measure the overall thermal envelope floor area. So that is just a nice clarification that probably resolves the fact that some folks are using external, some were using internal. On our platform you can use external, the middle of the wall internal, just with the flick of a switch. And the final one is just domestic hot water, guys. So effectively you've got to dump a heat load of 100 watts to represent a cylinder of hot water within your building if you have that domestic hot water within your thermal envelope. So a very small and nuanced thing, again, doesn't matter. This does not matter, okay? Whether it's there, whether it's not there, does not matter. It's there as a point of effectively inclusion within the model. Now, that was my top 10. I'm going to throw the camera on just for a second. I mean, did we Did I miss anything there? Was there any questions before I take a quick break and jump into the practical examples thereafter? Anything, guys?
No, I've got no questions. It's Diane.
Hey. So was that you have no questions, or you had a question?
Sorry, I have no questions.
Okay, cool. Sorry. Cool. Well, that's that then. I'll just wait for just a couple more seconds just to see if anyone else pops up. I mean, there is. What did? May I ask? Was everything pretty clear in terms of what I've just gone through? I know there's lots of information here, and not everyone's that familiar with VM1. Is there anything that anyone would like me to jump into to explain further? There's no poor questions. Anything there, guys?
Just one thing, Darren. Can you hear me?
Yes, I can, sir.
Just where are we at with Auckland Council? And you mentioned the PS1. Where have we got to on that? Because of late, we've been successful and they've been accepting our modelling reports that we're putting in. But when you said that Auckland Council are still asking for PS1s or can, that puts a bit of fear into our business.
Oh, I don't blame you. And look, I've gone through the process very, very recently of having a chat with them. And they've reached out to us for further training on VM1 and G7. And what that tells me is that they're getting to the point where they've had the PS1 argument so many times as well. And Auckland Council seem to be one of the few that are requesting PS1s, and it seems to be quite variable as well as to who's requesting them. But there is direction. There is a very, very clear directive that PS1s are not required for VM1 inside the council. So official direction that PS1s are not required. I cannot say what happens on a project by project basis, Lee. It's just too variable for me because I think that question has gone away. And
your understanding is that the higher up have got that directive, because we initially, as you know, we pushed back quite a bit in the when we introduced it, because we were getting it all the time, and we sort of went up the food chain, and like I say, it seems to have gone away, where we've probably had over 12 months without being requested anything. But when you said that they're still asking for it, it was sort of like, well, yeah, how do we address it? But you're saying that the hierarchy have actually come out and said that there wasn't a PS1 required.
Correct. Yeah, from my understanding, and the Auckland Council or the people that I'm speaking to have provided a request for retraining on VM1. So that's a good thing. And I don't know if anyone from Auckland Council are on today, but it's something that we'll go through. These things just take time, and I think ultimately there's just been a confusion over effectively what the verification method represents from a building code point of view. I guess I'm in two minds, to be quite honest, because I don't agree with the PS1, but I do agree with I guess a recognition of the fact that it's a more complex workflow, but from a code perspective, it's exactly the same as an acceptable solution. So it should not make a difference when reviewing from a council point of view, and we provided training to everyone through our platform. So that the fact that people are going through training, they're building up a level of expertise, that are delivering on a project by project basis, it shouldn't continue. But we'll see. Hopefully we'll get through this next version of the change, and it will be sometimes it takes 2 or 3 versions of a building code for people to get comfortable with the changes. And hopefully we're there now. Any other questions, guys? Before. Yep. Lee, did you? No. Okay, cool. Well, if there is none, I've got some practical examples that I'd like to go through, and I've got a model. the model has been set up for worst case examples. I say worst case for two examples, extreme examples for Auckland and for Queenstown. So just because I wanted to look at the extreme climate positions. Does anyone want me to, if anyone wants me to set up another model in this session, I will. Just shout out where you want it, maybe something that isn't in one of those locations, and we can go ahead and set that up. So if you want to pop something into the chat, let's do that. I'm going to just hold off for a couple of minutes while I grab a glass of water, and I'll be back maybe in 2 minutes time. So 2-3 minutes. If you want to jump off, grab a coffee, glass of water, go for it, and I'll be back then. Okay, I'll speak to you in a minute. Okay, that was enough time for a glass of water for me. I still have it here. Now, let's jump into some modelling on the platform. So we have a model that we can use here, and I'm just going to outline exactly what this model represents now. So here it is here. Move past the questions. Just going to model this here. It's the classic model that I use. You'll note that it has some external shading there, both from a surrounding building and locally here. And we'll have a whiz around that model in a second just to have another look at it, exactly what it is. And this is we can go through a scenario of looking at multiple climates. So as I mentioned, I've looked at Auckland and Queenstown just this morning just to set up some models, but we can look at Wellington and Christchurch as well. I've got some building envelope assumptions that I've thrown into the model. I'm just going to run through these. Walls, just timber studs with a 38% framing. So just a reminder there, we're going to pop in probably a bat of R 2.2 into those in order to get our R 1.6 in the walls. Slab, the slab ratio happens to be 1.6, so that's a calculation of the area to perimeter. And that renders an R value of R1 according to the code. Now, that's an uninsulated slab, and that's certainly not going to be a preferred outcome as you get into the colder climates. I've popped in a straight bat of R5 into the roof. Okay, so that renders a much smaller thermal bridge generally. Because you have less thermal bridging within your roof/ceiling systems than you would typically in your walls. So I've just popped in an R4.6 to represent that R5 bat. It could be a little bit lower, to be honest, it could be, but they are just assumptions for the time being. For the doors, we've just popped in an R0.3. Doors are terrible thermally, awful. So I've represented that value here, and we're going to put these into the verification method and see what happens. On the glazing side, just nominated R0.46. as a standard value, and 0.55 for the solar heat gain coefficient, representing aluminium thermally broken glazing. Could be, the numbers might jump about a bit in terms of the actual glazing systems proposed, but let's just stick with those as examples, and no direct external shading on the windows. We're of course going to use that NIWA climate file as mentioned earlier, and we're going to generate those heating loads and the cooling loads in the model. Now the design looks something like this. This is a design that's free to access, and I've just adopted this so we can go ahead and have a point of context. I haven't adopted the shading on it, and there it is there. We're going to learn a bit more about this, but effectively it has a couple of living spaces down below. We have the garage there. The garage is not included as part of your thermal envelope. So if you imagine there's a line, that internal line there is the actual external line here for from a conditioned space perspective. So the garage is not conditioned. And then we have 4 bedrooms up the top. I've assumed models both facing towards the north, as these models are, so a passive solar design methodology, but I've also flipped them around and faced this wall here toward the south as well. So I wanted to make sure that we could look at multiple scenarios. And let's go ahead and first of all we'll have a look at a couple of models from a verification method, and then maybe we can go ahead and create some more models. And I'm just going to focus on the New Zealand climate of Auckland and Queenstown to start with. Okay, so let me go ahead and bring the models over to this screen here. Just doing something over here on the right. There we go. Can I get just a confirmation there, guys, that we can see those? Just a thumbs up or something like that. I'm always paranoid about what people can and can't see. 2 seconds. Thank you very much. Okay, cool. There you go. Okay, so there it is. There's a model. It is what it is. That there is supposed to be a tree. It doesn't need to be in your model by any means. We can go ahead. I might just turn off some of this external shading just so we can kind of see this to start with. So there you go. It's a 3D model. It's been built out from a 2D model. You can import this into the platform should you want to, or you can draw this directly. To be quite honest, it doesn't take long to draw it directly once you get the hang of it. It's just whether you have an acceptance, a tolerance around redrawing modeling. Completely up to yourself. And this can be used for multiple things. If I go ahead, I'm just going to go ahead and get rid of that for a second. You can do daylight modeling, carbon modeling, design day. We're going to do H1 modeling method and the calculation method on this particular model. The walls, as mentioned, are all the R1.6. I'm going to go ahead and turn those off so we can see the internal walls and the glazing. The glazing are all 0.46 for the total system value or the construction R value. And then we have a solar heat gain coefficient. Much to Diane's disappointment, it's not called a G value, and it is 0.55. And then we have those roofs there. The ceiling in this case has a bat in it, R5, and that renders a 4.6 construction R value there. And we also have some roof systems there, and that is exactly the same. One thing I didn't specifically model in this case was this roof here, and I'm calling this a roof here just because it is the roof of a unconditioned space, being the garage. So we'll have to nominate a value for that. What else? And these slight overhangs here, if I pop on the wall for a second, I turned it off. If these have to be nominated as well because they're part of the thermal envelope. Okay, so we're going to look at this fairly easy. Now, here we are at the ground level, and effectively we've gone ahead and drawn outer zones, and we've given them a name. Okay, and we've got 1, 2, 3 that are living spaces. Okay, so these are just living spaces. You don't actually have to do all of this at all. You could put this into the one model, as I was talking about earlier. for multi-residential, I absolutely don't agree with it. For compliance purposes, for residential, it may be okay on some occasions, but you will lose the quality of information coming out of the VM1 model if you do. So it's kind of okay for the calculation method, but if you want to actually get modelling information out of your model, then you're not going to split this up into or have this into a single zone. It's going to be multiple zones. But if you're only doing the calculation method and you're really just looking for a compliance outcome, then it can be. But anyway, so you've got these, I guess, these transition spaces here. There's actually a bathroom space. I'm just going to nominate that as a different colour there, just so we can all see it. Then you've got the garage. Again, the garage is disabled from a thermal envelope perspective. It is out of scope. On the first floor, we actually have a couple of toilets there as well. So I'm just going to nominate those with the blue as well. We've got the grey for the bedroom spaces. And then we have this kind of walk-in robe here. I'm going to nominate that as well as a bedroom space. So there you go. That's what the model comprises. Not a great deal. Fairly simple from my perspective. For this model, we've nominated everything. Let me cancel that, save that. Never forget to save. We've modelled everything as per our discussion, or my discussion, trying to relay to you. We've got the 38% studs here, and the R1.6. The 0.55, actually that's the default now that I think I might have skipped over. They've just standardised the default for the solar absorptance if you don't have a value. You've got the roofs here, 4.6, that's taking into account the R5 batch. You can see that that's nominated there. Actually, I'll go back to the roof for a second. You've got two different roof systems here. You've got the roof system at the top of the building, and then you've got the roof system, any roof system that is not at the top of the building. Okay, a bit weird, but it's the fact that we use EnergyPlus under the hood, and it needs this information. For the slab, we've got the bottom floor. Or sorry, for the floor, we have a slab on the bottom floor. For the external floor, and the external floor is where you have a cantilever or a bit of an overhang. We've got an R value of 1.3 there. And that's actually also going to be for above the garage because it's deemed to be over an unconditioned space. And then you've got the internal floors. I've just nominated them as uninsulated, but they may be insulated from a soundproofing perspective. Maybe, don't know. I've just left it like that. And then for the windows, we have the 0.45, that should be 4.6. Let's just adjust that like that. And solar heat gain coefficient of 0.55. And what we're going to do is we're just going to add some openability there to the windows. And we're just going to say the windows are can be opened by 20%, let's say. Okay, could be less. I'm going to save that. And I'm just going to run the model now. Okay, so I'm just running the model based on this. The model is assuming defaults for the occupancy, for the lighting. This is all kind of set up in the default model for equipment, for infiltration, everything as per the code. This here is that 22 to 25 degrees. Again, it's set up for you, so you don't really need to touch this. There is a point of reference here in terms of what this value is here. And this is really just about, oh, sorry, someone hadn't been able to sign in. This is a value that hasn't been determined, and it's really the how much of the window that is open is openable back here. So we're saying it's openable by 20%. And then you have to go in and then nominate how much that 20% is open by. I know it's weird, but that's what you have to do. And once you nominate how much it's open by, and we're saying in this particular case it's open by 50%, so it actually means that Windows only open 10%. So it's open 50% of its openable area being 10% of that 20%. So anyway, it's weird and wonderful. Thermostat settings, again, a lot of this stuff you don't need to touch. You don't need to really care about any of this stuff if you're doing a straight push through for the VM1 calcs. Don't need to care about this. Sizing, everything is done for you, it's defaulted. And we've got a series of results over here on the right. Okay, so we can start talking about results straight away. This is for Auckland. How do we know? Well, I can go back up here and I can see that it's for climate zone 1, and it is showing results for the calculation method over here and for the modeling method. So if we look at the calculation method, this is not about the calculation method, but I just thought, you know what, you may as well look at the calculation method, and it's really useful sometimes to look at the quality of your model to make sure things are correct. Okay, so here, very familiar stuff in the territory of compliance within New Zealand. You've got the heat loss of your proposed building, heat loss of your reference building. This is exactly what the code describes. So effectively you can go back and cross-check all of this stuff here to say, okay, is that reference building correct? Great, it's correct. Okay, then I can now evaluate and be confident that the proposed design is also kind of being modeled correctly. And all we're showing here is that from a heat loss scenario for this particular design, probably driven by the fact that the R value of the slab is so low, is that we're failing in the calculation method. That wasn't the point. Okay, probably the more the point here is that you can look at the actual construction when you run a quick calculation method, because it's much quicker than a modeling method, and understand what you're actually modeling. So this green blob here is your condition space, okay? And this is just saying, okay, this is what I'm modeling in VM1 and in the calculation method. And then you can go and look at your walls and look at the nominated values. You can check whether everything's correct, okay? So this is really just about, hey, inputs are the most important thing. Get the inputs right, then you can start to get a measure and a level of trust on the output. So we recommend that you go through that process and get an understanding of everything that's been included in your model. And this is a quicker way to do it than keep running the modeling method. But the scope here is the modeling method. So in this particular case, the calculation method has failed in this particular case. The modeling method has also failed, but it hasn't failed by much actually. So we're going to transition over from the calculation method to the modeling method now, and I'm just going to show you a summary. So this is probably some of the stuff that, as Lee was mentioning earlier, that there is some challenges in terms of understanding the full scope of what's being modeled here. It's not super easy when you first look at this, and it depends whether you come from an engineering background or an architectural background. But effectively, this is just saying, as per the code, that we have space heating loads and cooling loads, and they must be, I guess, below a value, and that is the reference value there. Okay, must be less than 32.15, and that is the value you can see over here, which is that target value. It's pretty small there, just there on in the top right hand corner. And based on the floor area that's been modeled, we've got another value. This is our proposed design, and the story starts to narrate as you go down the screen here. And if we look at one thing at a time, let's turn off the cooling energy here. We can see that the proposed design is using more heating than the reference design, and that's a part of the narrative. That's a part of where we can improve the design and get a better outcome. When we look at the cooling side of things, we can actually see that the proposed design, and this is not by design in terms of to support this narrative in any way or form, it's just chance, that the proposed design here is actually using less cooling than the reference building. So the narrative here is that the opportunity lies somewhere between improving your heat loss in order to, and your cooling in order to get this over the line. But there's not far to go, because we're only comparing a target value for space heating and cooling load of 32.15 against a target value of 32.91. So there is not much in it. And even just a quick look would tell you that just upgrade the slab or something like that, or you could even just change the solar heat gain coefficient a tiny bit. These types of things are what you'll need to look at. Okay, so this is the report. You can print this out, put your branding on it, blah blah blah. You can do all of that, and this is what goes through to council, and it is detailed. What I recommend in all cases is that you write a letter or a brief summary, you provide your drawings, and then you drop this into the back as the proof of where you have substantiated your compliance findings. That's what I recommend each and every time, because that's the best way to do it. And if you've undertaken training on the platform, show that training, show the certificate, show the competency of the user that has used the platform, and that's the way we find you get the least resistance and the most amount of confidence that you know what you're talking about when it comes to compliance. All of that is pretty easy. Now, when it comes to the model itself, we can have a look at the model. And this is where we get a lot of information about the proposed design and the reference design. Okay, so I'm just going to click between the proposed design and the reference design, with the reference design being the thermal envelope described within the VM1 calculation method, and the proposed design being your proposed design that you're comparing against. Okay, is anyone unclear at this point about that? Because I just really want to make sure that everyone is cool, that where we understand the basic principles of what we're doing from a reference to the proposed and the space heating load and cooling load. Is that clear? And there's no issue if it's not clear. I'm just, when things go cold and I don't get feedback, I always get a little bit paranoid at this stage. No, sounds like you guys are completely across it. Now, once you get into this stage, we want to look at the proposed design, and we're asking ourselves, how are we going to get that additional benefit? Now, you can look at a whole heap of things, and I'm going to keep it easy. You can look at heating energy, and of course you can compare that against the reference building. So you'll be able to do that. Do the cooling energy. Compare that against the reference building. So you can do that if you're really into the numbers. What we find the most beneficial thing to do is probably to go over here to your zones, and then you can see the model itself. So you're not deep into the numbers here, and you can select each zone and say, okay, what's happening in each of these zones from a heat transfer perspective. So if you wanted to select one here, you can select that one and you can see all the information. And if you really want to engineer your way out of this, you can export the data and work out exactly what's happening in the model. You can export images as well to support your findings, etc. So you can do this and pop them into an email to communicate them with the design team, etc. Probably the best thing for folks is looking at these selections over here: wall, roof, wall, floor, ceiling, roof, etc. If I start with floor here, we can go into what's happening at the floor, and then maybe just select a floor. Okay, so if I can get your attention up here: heating gain 2.83, heat loss 26.01. So there's kind of this net heat transfer here of negative 23.19. We're almost constantly losing heat to the ground via the slab. Okay, so it seems very obvious that that's a point of improvement that we could undertake. On the ceiling side of things, let's go ahead and select the ceiling. Remember, this is a total R value of 4.6. And again, not by design, it's more by intuition, to be quite honest, but you can see that there's effectively no heat transfer through this ceiling system in Auckland with this particular design, because effectively the heat gain and heat loss are exactly the same. Okay, so this is telling us that this is perfectly designed, this particular ceiling. Again, I didn't do that on purpose. I'm just really good at my job. That was a joke. This is a big one. Okay, and this is where we really need to be cognizant of what we're doing from a design perspective. Now, over in calculation methodology land, we know nothing about the impact of heat gain through our windows. We know nothing about it. We're completely uninterested in that question, and it's probably one of the most important questions you can ask in your design. Because at the moment, the calculation methodology tells us that we failed, fine. It might tell us that we pass, but it tells us nothing about how much heat transfer there is here. So if I'm just selecting one of these windows towards the north, okay, just one, couple of, it doesn't make a difference which one I'm selecting. Actually, I'll select one here, and you can see one here, different color. The lighter color means there's a lot less heat transfer, okay? So if I select this one here, I can see the heat gain is 390, the heat loss is 66. Great, we've done a great job from a heating demand perspective. We've improved the design. But from a heat gain perspective, that's pretty lousy. Like 390 kilowatt hours per meter squared is a lot of transmitted heat through that window. And that means there's a significant design opportunity to improve that without necessarily impacting the introduction of heat during the winter period when we want it introduced into the building. What this intuitively tells me is that the comfort within these bedrooms is going to be questionable, because these bedrooms are not going to have their windows open during the day. They're just going to be left typically. And when you go into those rooms at night, they're going to be stuffy, they're going to be hot. They're going to need the spaces purged, because the building is going to be fairly well thermally insulated. And how do we know that? Well, we can go to the air temperatures in the space and start to see that there's quite a lot of temperature points greater than 24 degrees. Okay, so it's telling us that, hey, actually there's more that needs to be done in these spaces than what the calculation method is telling us at all. So there's a major value add, and there's a lot more stuff that we can go through here. I just wanted to get to the point where we can understand exactly what the difference is between the calculation method and the modeling method before we kind of continue to look at the verification method. So we've nominated our building envelope, we've run the reference building, we can see the result. We have not complied in both scenarios, that's fine. But there is this hidden narrative that the calculation method will never tell us. So if you're jamming your designs through AI, going through simple spreadsheets, you are not designing your building in any way or form to be 100%. It's just not designing a building. The only way you design a building is you design a building by understanding the narrative about what's happening in the space. And any risk that you generate through the calculation method is effectively your risk to own, because you haven't looked at the design in enough detail from my perspective. As we build better, we must detail the design. And that's all I'm going to say about it. So that is simply a passive solar kind of design. Now, we could flip the building, and we could flip the building and say, what about if we turn this building 180 degrees? And it's very easy to do on the platform. You can kind of go ahead here and just say, okay, I'm going to turn that 180 degrees. Instead of doing that now, I'm just going to show you the result, because it's easier to show you the result. And then we can kind of flip between the two. And there's not a huge amount of difference between, to be quite honest. Let's flip between the two. This is the north-facing version. This is the south-facing. Okay? So what we can see is that the heating jumps up a bit. The cooling jumps down. But not a huge difference. You'll probably find a big difference in the numbers as we go to different climates. So I'm going to jump in now and show you the difference between this building with exactly the same specification in Auckland and Queenstown. This is the difference. Okay. I'll just flash between the two for a second. 32.91. Doesn't make a difference whether you understand the number itself. The important point is that you can see that this number goes up as we go to Queenstown. Okay. And that's because Queenstown is a heating dominated climate, you know. So the solution here is going to be effectively all around the thermal envelope itself. So while in Auckland you have a solution that is going to be a mixed bag of things, like looking at small improvements to thermal envelope, but looking at the shading and resolving your cooling loads. In Queenstown, you're not so much worried about that. What you want to do is really improve the performance of the envelope, and by the fact that, you know, it's so much higher here, let's have a look at the proposed design to substantiate why. So if we go ahead and go into the zones again, let's look at the same sort of thing. So what does the ceiling tell us this time? It's still not bad, actually. It's not bad. The floor. So negative 55.46. Let's just jump back and just be fair on everyone, and we'll have a look at exactly what that is again for the floor here. And which zone did I select? I'm going to select that zone there and there. So here we have negative 23.19. Here we have negative 55.46. So anyone can see that there is a significant amount of heat loss. And what happens with that, of course, is that your surface temperatures are going to drop down, and you're going to need to improve that slab as you go to Queenstown. That's probably not news for anyone, but it's there just to show you where the narrative will lie. So if we go ahead and do that, we can go ahead and say, okay, we're going to commit to that, and yeah, our floors should 100% be way up here. So let's say 1.6, okay? And should you want to go ahead and have a look at the slab calculator, you can go ahead and do that over here, and that will give you a resultant total R value to pop in to the design. Now I can't remember exactly what the slab perimeter length and area was, so I won't do that now. So you'll have to do a takeoff for that in order to use this. But effectively, we're theorizing that we're going to push that up to 1.6. Okay, so we could do that. We could also jump into the windows and do something very similar. We could say, do you know what? We're going to go wild. We're going to go triple glazing. And what we're going to do is we're going to put in a UPVC frame, and we're going to change the performance of the glazing. It's going to go way down if it's triple glazing. Actually, what I'll do something double glaze. So I'm going to do something double glaze and pop in a really high performance kind of 1.2 center glazed and take us to 0.63. Okay, so UPVC now 0.63 across the board, and we can pop that in there. Okay, we're just going to make those two changes, and we're going to see what happens with both the calculation method and the modeling method. So we're going to run those now and see what the results are. So the calculation method, bang, that's back. The green across the board is telling us, hey, we've got results here. Everything is complying. And this is one of the reasons why I think the calculation method is going to live on, because we can get outputs there. How far over the line is it? Well, it's quite significantly over the line, as in complying. Here we can see the reference building, 395.07. That's determined there, 395.07. And then we have the proposed design, 374.61. That's significantly over the line from my perspective. And there is no question that that would be the method that would be undertaken, I think. But we're going to wait for that modelling method to come back. I'll take some questions if there are any at this point in time. Just if you'd like me to explain anything that I've gone through, because I appreciate that I'm going through lots of information. We're about to draw down on our time. I'll also do just another shout out. So if someone wants us to look at another climate zone, feel free to request what that is, and I'll jump in there. And there you go. This is the modelling method. Diane, did you want to jump in there quickly?
Oh.
Diane is my co-presenter, by the way.
Sorry. I guess I would have thought that there would have been cheaper changes to make than going straight for UPVC. But,
maybe.
So I guess that's all I wanted to say to the audience
what would they be?
A better way to build the walls,
Yep.
just playing with the U value of the walls.
Yeah.
The floors can be quite expensive, but
They can, yeah.
But
To be clear, the changes that I've made are very consultant-based changes. I've just thrown great numbers at it and look for a solution. But we'll run through that example, Dan. We'll do more practical changes. So let's call this our high performance outcome, and we'll go back and we'll see exactly what a more practical approach to compliance actually looks like. So let's pick up on what Diane's saying, and we'll probably just finish up after that then. So I'll just finish up on the modelling method here. It still hasn't complied. So what is my point? My point here again is that, hey, the calculation method looks like it's a stronger method, that's not to state that the results within the modelling method are not advantageous to design. You still want to be able to be assured that your design is, I guess, what you expect it to be, and you can go ahead and look at the glazing again, look at the heat transfer, see if that's what you expect it to be, look at the temperature profiles. Much better. Let me have a look at temperature profiles up here. They are better, but I'd probably argue that the solar heat gain coefficient is still too high. 0.55. I have a real bugbear with that solar heat gain coefficient. It seems to be the standard value that gets thrown around, and I think it leads to overheating. I think it should not be that high if you are not designing to a very, very high performance building with the amount of design that is required to achieve a comfortable outcome. But what we can actually see is that there's a hell of a lot of hours below 20 degrees, and that's because the set point within the building, i.e. the point in which we turn the heating on, is 18 degrees. So that's the reason why that is so high. So the calculation method, saving the day there. Let's go ahead and pull our changes back now. We'll just run this one more time. It's a good example as any. So we'll bring the glazing back. We can probably insulate the slab perimeter or something around 1.3, and for the roof we can leave the roof, there's no benefit there. And the walls, let's build out the walls, let's reduce the thermal bridging within the walls, and we'll render an total R value of around 2, something like that. So a small change there. What else did I change? I feel like I changed. No, that's fine. I think that's it. I'll leave that there. Actually, there's no, I don't know why. That's no operability on that for some reason. I didn't save that. I'm going to rerun that. There you go. So let's look at it. We're looking at the calculation method and the modelling method again. The calculation method is going to come back quick. There it is. So there you go. I mean, to Diane's point, where we're just hitting the right numbers from a calculation method perspective, and the modelling method is going to fail even further. So gives you a heads up. In a colder climate specifically, it's going to become harder and harder to use the modelling method. I think if you're just dumped a building with a certain design and you're told, hey, let's kind of make this work, you need to design with the modelling method in mind. But the modelling method does provide a jump-off point for so much more value, so much more design optimization, that it can't be ignored. So it's a mixed answer that I'm providing here. I'm saying the calculation method is very, very, very likely what a lot of people are going to use because it's so much easier, but you should not use it without further substantiation, or you will leave yourself open to overheating scenarios, additional risk that you really don't want to absorb yourself, because at some point there is an expectation that the overheating risk is being reduced via the changes that have come through. There you go, we've got a failure again on the modelling method. But I don't think that's the case. I think overheating risk is going to continue. It's everywhere. It's in Australia, it's in the UK, it's in the US, it's in New Zealand. And if you rely on a method that doesn't take that into account, then don't expect there to be any change. What was that Einstein thing? If you keep doing the same thing, it's madness or something? I forget what it was. But anyway, there it is. I am going to be quiet. I am going to thank you for your time. A lot of you have been on here for a while. Ian, Bipin, hey Diane, Lee, there's a bunch of people I know here. Yeah, I hope you're all doing well. Feel free to shout out to me whenever you need. I'm available on the ticket system. Happy to answer your questions. I think that's me wrapping up, isn't it? I think I'm done. If you would like to fire over any last minute questions, feel free to do so. I think I've almost kept this on time as well, which is an absolute miracle for me, because I do tend to waffle, as you know. Done. Okay, guys, that's me. 5 minutes left in my meeting. I'm good. Diane, thank you for that. Thank you to my co-presenter, Diane. Appreciate that. Maria, thank you for the sound check. Lee, thanks for the questions. Thanks, Max. Thanks, Josh. Thanks all. Appreciate your time. Happy to stay on for a couple more minutes. Should anyone want a private little question time? More than happy to do that. Let's stop that recording.